So the second round of things, the sort of second type of setup we're going to deal with here are combinations of tangent and secant. They have a similar, similar means not the same, but, related relationship to sort of the way that sine and cosine interact. Sine and cosine, right, kind of are the derivatives of each other. And secant and tangent are also kind of linked up as far as what the derivatives are, but it's not as simple as just the derivative of secant is tangent and the derivative of tangent is secant, right? The derivative of tangent is secant squared, and the derivative of secant is secant times tangent. So those derivatives mean that, when we have something in this form, right, it kind of affects a little bit what the goal is. In the last section, right, for sines and cosines, effectively what we wanted was, sine to the something times a single cosine, or flipped cosine to the something times a single sine, right? You want a base function sort of times its derivative. So for us, the kind of forms that we're trying to hit would be things like tangent to a power times secant squared. You could do a u sub then where tangent is u and you'd be good to go. Or, right, secant to the power times secant times tangent. So that one's a little strange because you have secant and then like another secant. So we'll obviously talk about what the implications there are. If that's your setup, right, secant as your base function would be your u, and then that would be your derivative, and you'd pretty much be good to go. So let's kind of quickly just review what the derivatives in the kind of nice version of the formula would be before we get into the actual kind of cases as far as like what does this mean when you have even and odd powers in different places. We're going to approach this kind of similar to what we did for sines and cosines in some sense. So here, so say I've got, right, the integral tangent to the 6 times secant squared. Oh, dx, of course. Sorry, I forgot my dx. How could I? Right, so the move here, right, what I have is tangent to a power, and then secant squared would be the derivative. So we're just going to let u equal the tangent of x, right? So then my derivative du dx is secant squared. So dx is du over that. So this will just be, right, integral u to the 6, just like a nice u sub. This is the kind of thing, right, that we've kind of done already. I don't know, I can't remember off the top of my head if officially we've sort of seen ones like this or not. But it kind of fits with our general rules, right? You want to pick stuff that's raised to powers, right? So tangent raised to the 6, that's probably a good candidate for you anyway. The secant squares here cancel each other out. So really all I'm dealing with is, right, the integral u to the 6 to u. So my antiderivative, just a nice power rule on u. And then rewritten, right, 1/7 tangent to the 7 of x plus big C. So if I can hit that form, right, if I can get however many tangents times like a secant squared, then I'm pretty much good to go. Then I'm golden. Not any real issues from there. The secant version is a little bit different. And actually what I'll do is, say you've got something like, secant 4 of x times tangent x dx. Maybe I should have put the tangent first. I guess it doesn't really matter. So you're going to be given these, right, just in terms of like secant and tangent. It's not going to start out written like this where you have one of the secants connected to the tangent and then the rest by themselves. You would never have something written as secant to the 5 times secant times tangent. It would just be written as secant to the 6, right? So in this case, maybe we've got secant to the 4 times tan x. So the move here is just to say, okay, what I want to do is just borrow and kind of sort of resort one of these secants over with the tangent, right? Secant x tangent x dx, right? I'm just trying to recognize that form and then group those two together. So then the move here is let u equal just single secant of x, right? Because then your derivative would be secant x times tangent x, which then of course means dx would be du divided by that whole thing. Right, as always, it's really just a matter of kind of recognizing these forms and trying to kind of set yourself up for success. So this for us will be what? So u cubed secant x tangent x. It's just kind of a strange derivative. You know, I guess you hit a certain point in a Calc 2 class and you're saying, I don't know, everything here just seems strange all the time. And that's fair. Things can be kind of strange. So secant tangent, right? Sync up, these guys match. So really what I'm dealing with here is u cubed du. So then I'm just doing power rule again. So 1/4 u to the 4 plus big C, and then of course the original u was just the secant function. So, you know, the move here, this, you know, these sort of two setups are going to be kind of the basis for what we would look for and kind of how we would approach this. But let's save those approaches for the next video. So we'll kind of dig into these a little bit deeper, and we'll go kind of case by case coming up next. So that's the basics, right? That's kind of the forms that we're trying to hit. So the question is, you know, what kind of powers do we need, even and odd, on the tangent and the secant to be able to sort of slide into some of these different forms? So see you in the next video to find out.